Okay, what we're going to do today is we're going to work on area as a model, and then we're going to take that area model, and then what we're going to do is we're going to relate it towards factoring, which is our primary method of solving quadratic equations. So I'll try to make these connections here, and then hopefully we can see them as we build through this chapter, which will be chapter 4. Okay, so if I want to represent multiplication as an area, I mean, this can be pretty easily represented using a rectangle or a square, right? Because I know if I have 3 times 2, well, I think we all know that this is equal to 6. We can just take a little rectangle here, and if I make this 3 units here, this means I'm going to split it into 3 definitive parts. And then if this is 2 units, I'm going to split this into 2 definitive parts. And the reason why 3 times 2 is, 3 groups of 2 or 2 groups of 3, 1, 2, 3, 4, 5, 6. Okay, and this really can work for any multiplication of it, that you do. It can be represented using an area model, specifically with rectangles. Okay, so here might be a good idea for you all to try and represent the same model here with 6 times 3, which, in case you don't know, is 18. So go ahead and try this on your own. Okay, so here I'm going to go ahead and set up my rectangle. If you're checking it with me right now. Okay, and we're splitting this into thirds. So this top length here will be 3. All right, this is bottom part here. Thirds. This will be 6, and then we know that this is equal to 18 because 3 groups of 6, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, and so that's just like basic multiplication and how it can be represented with area, and just really why 3 times 2 is 6. Most of you probably already know this, but let's just kind of dive a little further. What if I have like 18 times 13? Okay, now this one could be done the exact same way, but, for me, I don't really feel like this is quite a bit of work here with just 18. I don't really feel like drawing 18 individual columns and 13 individual rows and counting up all the boxes. That's pretty inconvenient. But what we can do is we can use little parts of what we know about multiplication to be able to represent this still with an area model. So what if I create a rectangle? Okay, and I'm just going to create a rectangle like this. Okay, and I can break up this top part. So if I'm going to say that this top part here is 18 units, I can break this up. I could break this up, maybe not quite at half, right? I could say that, hey, this length here is going to be 10, okay? And so then if that length there is 10, this length here would have to be 8. Right, so what I did is I split this into 2 individual rectangles, one with a length of 10 and then another with a length of 8. Okay, so I have this split up pretty evenly, but I can do the same thing with 13. So if this is 13, I could break this up into anything. So it didn't have to be 10 and 8. I could have done 15 and 3 or 9 and 9, whatever's convenient to you, because that's just how we're going to decompose it, right? So this one here, I can break it up. Okay, and so when I do this, I can say, hey, again, maybe I want to break this up into 10. Make this 10. That seems pretty convenient to me. And then if I broke that up into 10, what would this part be broken up into? It would be broken up into 3, right? Because 10 and 3 add together to be 13. So if this whole thing is 13 and from here to here is 10, that means from here to here would be 3. So how is this beneficial to me? Well, how this is beneficial to me is now I can use smaller numbers or little parts to actually break up my multiplication to make me to be able to do this without a calculator. So for example, what's the area of this rectangle or square right here? Well, we know it's got a length of 10 and a width of 10, so that means this is a square because they're both the same. So that means that this is going to have area of 100. Okay, so then what would this area be? Okay, so we have a length of 8, but then a width of 10. Okay, so then this would be 80. Okay, what about down here? We have width of 3 and a length of 10. This would be 30. And then 8 and 3, so this is an 8 by 3 rectangle. So an 8 by 3 rectangle would have an area of 24. Okay, but these are all just individual areas. What if I still want the area of the entire thing, right? So if I want the area of the entire thing, I just have to add all of these up. So here I would just have to take 100, 80, 30, and 24 and add them together. 13. Okay, so the total area here is 234 units squared. Okay, pretty straightforward, right? And again, you could have decomposed this however you wanted. Okay, so I think it's going to be beneficial to you all if you pause the video right now and you try this one on the right and decomposing this however you wish, and then seeing if you can get the area of 19 times 17 without actually having to use a calculator. Okay, so I'm assuming that we've already paused the video at this point, and I think most common for people to do is something like this. Okay, and so if this is 19, I think most people are inclined to break this up into 10 and 9, and then similarly break this up into 10 and 7, making this 100, this 90, this 70, and so that's 63. And then when you add it all up, 1622. And to find out that this is 223. Okay, so actually, although this seems pretty basic and honestly something that maybe we probably already should know by now, it actually is incredibly important because what it's going to do is it's going to help us, one, figure out how to multiply binomials. You may have noticed this is similar to the method we call the box method that we've done before. It's also going to be very similar, this setup, and how we factor, and factoring is kind of the reverse of the box method, which we'll kind of see as we go. So let's actually just go ahead and we are going to continue to show how this multiplying binomials can be used in the same box method. We're just splitting up our, we're just going to split up our binomials that we have here. Okay, so here what we can do is actually we can start introducing of tiles. Okay, so here what we're going to have is algebra tiles. So this first one here, blue square, is going to represent x squared. So anytime you have like an x length times an x length, you are going to have x squared. Okay, and then the opposite of that, the red, would be negative x squared. Okay, here what we have here is just x. Okay, it's a length of x and a width of 1, so this area here is just 1x. Okay, and then the back here would be the exact same thing except for negative 1x. Okay, and then these little tiles here, we have 1 and negative 1, area of 1 and area of negative 1. Okay, so what we're going to do is we're going to go ahead and model these with the tiles, and then we can go back and use the box method. So here we have x plus 2 times x minus 3. So what I'm going to do here is I'm going to zoom out just a little bit. Hopefully I don't destroy everything. Okay, and so what I'm going to do is I'm just going to model this here. So I have a length of x plus 2. So what represents x? Well, these little things. This is x. Okay, and I'm going to put this here. But then I need x plus 2, but this is just x. Okay, so as I see this here, I need to add 2 little 1-unit squares there to represent x plus 2. Okay, so as you see this is x, this is 1 and 1, making this whole thing x plus 2. Okay, we can do the same thing, but the next one we're looking for x minus 3. So here I'm going to have an x, and then minus 3. So that's going to be 3 little red ones here. Okay, and so then basically what we can do is this is my length, x minus 3, and my width, x plus 2. What we can do is we can create an area out of this, and almost it feels like what fits best. So here if I have x and x together, x times x is x squared. So that fills up this little rectangle here. X times x would be x squared. Okay, so what about if I have x times 1? Okay, x times 1 is going to have an area of 1x. Okay, and then I go x times 1 again, that's going to have an area of 1x. Okay, and then we still have this whole missing area, right? So I know that if I have this first row here, this is x squared and this is 2x, but then I still have this area over here. So what if I have x times negative 1? Well, that's negative 1x. And as you may have guessed, that is going to be the same here and here. Now what about this upper part, right? Well, this looks like to me as we've kind of got this combination here. We've got these combinations here. Okay, we have these combinations are going to go here. Now we just have to kind of mash these together, and this is 2 times negative 3. So 2 times negative 3 is negative 6. Okay. So these algebra tiles here actually represent literally what the box method is doing for us. Okay, it's a great model for it, for us to see the area if we're representing our multiplication, which that's what we're doing. I mean, if we look here, we're multiplying two binomials. It comes up with this. So now I can kind of push this off to the side. And then this is my final result. This is the rectangle that x plus 2 and x minus 3 would represent. Let's figure out what it is. So I have x squared, and I have minus 3x. I have plus 2x, and then I have minus 6. So what are those all going to combine to, right? Because minus 3x and plus 2x, those are going to combine in together into minus 1x minus 6. That's what it's equal to. Okay, so we know that this is the answer. So now that we've seen how the tiles model it, let's go back in and actually use the box method to see how that will work. Okay, so if I did the box method, okay, I can split it up, and I can go x and then 2 here, right? If this is length x and this is length 2, this is going to be at length x plus 2. So if this is length x, what would this length need to be? It would need to be like negative 3, which might be kind of hard to represent, but algebra-wise, it fits right in perfectly. Okay, and so then just kind of like before, x and x is x squared, x and 2 is 2x, x and negative 3 is negative 3x, and negative 3 and 2 is negative 6. Which is, if you notice here in blue, is the exact same thing as what we have here, meaning that this all together is x squared minus x minus 6. Okay, now what I really want you to do is I want you to pause the video, and I want you using tiles or the link I have online that will link you to like a digital version of these tiles. I would like you to do the remaining 3 that are on this page. Okay, and then what I'll do is I'll go ahead and share my end result, but I'm not going to work through every one with you. I want you just to work through each of these with the tiles to get your answer. You do not necessarily need the box method. If you want to use the box method to check your work at the end, that's great, but unnecessary. But otherwise, go ahead, pause the video, use the tiles to go ahead and try these out. So I'm assuming that we've already paused the video at this point, and you're just kind of seeing what your answers should have been, which this here, x squared plus 3x plus 2 is your answer for the first one. This one here is x squared plus x minus 2. And then this one here, x squared minus 7x plus 10. Okay. So hopefully you use the tiles to build these, because what we're going to do now is we are going to go in reverse. So what do I mean by that? That means I'm going to be given something like this. All right, we're going to be given something like this, if I can ever build it back correctly. Those need to be red. Okay. All right, we're going to be given something like this. And then what our goal is going to be is say, I know this is the area here, but what's this side length? And what's this side length? You may notice right now it's really not that difficult. It's length x, and then 1, 2, 3. So this is x minus 3. And this is length x, and this is length 2, so this is length x plus 2. But the problem is we might not have the rectangle built. We just might be given something like this, and then we have to build out of that. So let's go ahead and see what that's going to look like. Okay. So I'll go ahead and try to model the first one for you. Okay, at least maybe get us started. Okay, so here what I want to do is we're going to work backwards. Now what we're going to be given is this is the whole area that we're going to be given. So we're going to have all the pieces that we need to actually build the rectangle, but then we have to figure out what the length and the width are. So here, if you look here, I need 1x squared, so I'm going to take a 1x squared here. And then I need 6 x's, so I need 6 of these. 2, 3, 4, 5, 6. Okay, and then I also need 8 ones. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so now that I have all my pieces, my goal is what I need to do is I need to create a rectangle the best I can. And then we're going to find the side lengths from there. So now the best advice I have for you is, one, just as I did, get all your pieces out that you need. And then in best practice, is going to keep the x squared in the bottom left-hand corner. And then the ones, wherever those end up, the ones probably need to be in this quarter. It's the x's that you're going to have to move around. Okay, so let's go ahead and try this. So I can maybe try, I don't know, something like this. We're going to put all of these 6 x's just right up here, meaning that I would have a length of x and a length of x plus 6. X, and then 1, 2, 3, 4, 5, 6. But the problem is I can no longer create a rectangle because these ones just don't fit anywhere. They don't have any way for me to actually create a rectangle. Because I know any time I multiply anything, numbers or variables, it can be represented with a area of a rectangle. So as you can see here, this just doesn't fit. It just doesn't work. Okay, so I have some options, right? So all of my x's don't have to be here. They can be up here as well. We've already seen examples of that. The example I did previously when we were multiplying. Okay, so then we can maybe even do a little thinking ahead here. So what if I go ahead and I'm just going to take 1x and I'm going to shift it up here. Okay, so then now I can really start filling in parts, right? So this looks to be making a very good rectangle, but the problem is I just have these 3 ones left over. They don't create a rectangle the way it's currently configured. And if you think ahead to how the box method works, like I know I have 1, 2, 3, 4, 5 here and 1 here, that I know that this area up here is going to have to be 5 because 1, 2, 3, 4, 5 times 1 is going to be 5. So we knew I knew that was not going to work. So I can just keep kind of maneuvering things around. So what if I go up here? Okay, so now, as you can see here, they kind of all fall into place pretty nice and neat now. Okay. Now I've created a rectangle and I've used all of my pieces. So this is the combination that's going to work. And these combinations are unique to the area. So this will be the only answer. It's never going to have multiple answers. So let's think about what my length and my width are, because that's what I'm interested in. Is I want my length to be x plus 1, 2, 3, 4. Okay, so here this is length x, right? If I go down here, this is length x. And then this other length is length 4. 1, 2, 3, 4. And then what's this length going to be? This length here is going to be x and then 2. So what does x squared plus 6x plus 8? This is my area, x squared plus 6x plus 8, but what's my length? It's x plus 4 and x plus 2, and that's what I'm interested in. So this is going to factor into x plus 4 times x plus 2. Okay, That is the combination that will work. So what I'm going to do now is I just want to talk very, very briefly about the negatives, okay? Because what if I had, if we look here, okay, hopefully you all understand how I got to here, but let's go back one page. And let's recreate this one here. So if I wanted to go work backwards, this is what I want to get. I have x squared minus x plus 6. So I would have an x squared. I would have 1 minus x, and then 6 negatives. Okay, so as I'm going through and I'm trying to build this rectangle, like there is just literally nothing that's going to fit. So what we can do is introduce a sneaky 0. So what do I mean by sneaky 0? What I mean by sneaky 0 is I can introduce one positive x and one negative x together. And let's talk about why. Why can't I just blindly introduce one negative x and one positive x together to create 0? Well, the reason is if I take x plus negative x, those are opposites of each other. Just for the same reason 2 and negative 2 add to 0, they cancel out. The same thing works here. So what I can do is I can keep my negatives together, but then I can throw a positive up here. And so then now I'm a little bit closer to building my rectangle. I'm still not there. So to be able to do that, I just need to introduce another sneaky 0, as you can see here. And then I would throw the negatives with the negatives and the positives with the positives. And then now you can see it fits. So you need to be careful about ones that involve negatives, because they you may have to introduce sneaky zeros. And if you look here, x minus 3, x plus 2, which is exactly what we ended up having. Okay, so you have to be careful about that. All right, so let's go back to the page we were on. What I want you all to do now is I would like you all to go ahead and try each of these. I want you to build the area and then try to find the side lengths, the length and the width, which this process is called factoring. Okay, so I want you to go ahead and try that and see if you can find the factors such as I found here for each of these 3. Okay, when you're done, I'll have the answers, but not necessarily the builds of how I got that, okay? So, actually, you know what? I take that back. As I go through to check each of these, we will have each of these built for you, okay? So go ahead, pause the video, and go ahead and check these on your own. Okay, here's the first one. This one's not necessarily perfectly set up, but let's go ahead and check and make sure I have x squared plus 10x plus 9. So x squared plus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10x, and then 9 ones. 1, 2, 3, 4, 5, 6, 7, 8, 9. So the combination that worked for me and should work for you is I'm having x plus 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then x plus 1, right? So here's my length x, here's my length 1, and then that will fit perfectly into this, making my factors x plus 9 and x plus 1. Okay, now for this one here, we're going to end up getting x minus 3 times x minus 4, okay? So here I have length x minus 1, 2, 3, 4, and x minus 1, 2, 3. And as you can see, it fits. Now let's just talk about real briefly why these are all positive 12, besides the fact that it gives me positive 12. If you think here, we have x minus 4 along the bottom here, and then minus 3 along the top. So if I have minus 4 here and minus 3 here, when I multiply negative 4 and negative 3 together, I do get a positive 12. So that's why that would end up being the case as it is. Okay, for the last one, I'm going to go ahead and do this one from scratch here. So I have x squared minus x minus 12. Okay, so here's my minus 12 right here, and here's my minus x. So I set my x squared down, and then I set this with it, and really, I can visually already see there's no way that these ones are going to fit at all. So, just as I mentioned before, what do we have to do? We kind of have to introduce a sneaky 0, right? So if I go ahead and I can introduce a sneaky 0 here, this is 0. So let's talk about the importance of that. It's 0, so if I add in 0 to this, have I changed the value at all? I have not, because anytime you add 0 to anything, it doesn't change the value. It would be like if I guaranteed that if you guys all behaved yourself well in my class, that I decided to give you all $0, that would be no motivation because it's not adding anything. It seems pointless, right? But this one is different because it does allow us to factor, so it isn't quite pointless, but it doesn't change the value, which is very important. Okay, so I'm going to introduce a sneaky zero here. I'm going to throw my negative with my negative, my positive up here. And really, I still can see I only have space for 2 of these. So this really isn't my combination. So that means I just have to add another sneaky zero. So I'm going to add in a sneaky zero here. And we got more space for more negative 1s. But still not enough. So then we have to go again. I think this is going to be the one that matches. And it is. So as you can see here, this is indeed my combination. Let's go ahead and kind of nudge this stuff together. Okay, so here's my combination. We just need to think about what's this length. It's x minus 4. Okay, so here we have x minus 4. And then x plus 1, 2, 3. And that's the combination. Okay. All right, the only thing I'm going to ask you all to do left is on this back page. If you look, each one of these is called a factor. Okay, and then this is like our area or our trinomial that we're dealing with. These things are equal to each other. They're all literally the same. Okay, now what I want you to do is I want you to look at each group of factors and then the trinomials that they go with. Okay. And what I want you to do is answer this following question that I will address at the beginning of the 4-1 lesson. In your own words, what is the pattern that you notice that will help you factor without the use of tiles? So what I'm asking you is how can I know that x squared minus x minus 12 is equal to x minus 4 times x plus 3? Okay, how can I know this without ever actually having to get a single tile out or use a single tile? Okay, there's a pattern here amongst these binomials in the originals. Okay, so go ahead and think about this, test this out, put some thought into it. It will pay dividends later on. Okay, but otherwise this question will be addressed at the beginning of the 4-1 lesson, and I will see you then.